All right, thank you so much. Thank you for the invitation to come here and talk to you about a benchmark we're trying to put together for HPC plus AI. And I want to thank my colleagues who've been doing a lot of the work here. And we've actually had a lot of collaborations with some of our Rican colleagues, particularly Wahib and Rio Yokota. So let's get started here. So we want to talk about how can we develop a new benchmark for testing large-scale HPC systems, particularly when they have unique AI workloads. And when those AI workloads go beyond, we just want to train an LLM or run an LLM to do sort of those kinds of tasks. When we want it to be a scientific-based AI model, we call it AI for science, SciML. There's a lot of different things here. But how do we actually develop new benchmarks? Because it's actually particularly challenging. So this has been a long time in planning, but a key component of it you'll see in a moment here was actually inspired by a previous R-CCS symposium a number of years ago on training models with fractals as a generated data set. And that was a key component that I've been missing for some number of years while thinking about this. So that was really exciting. So when we talk about benchmarking, we really want to focus on accelerator to accelerator benchmarking. So a lot of HPC codes come from a CPU-centric where they offload to the accelerators. Most AI workloads are running on the accelerators. They expect to communicate and move their data explicitly from the accelerators. And that means the pathways you want to go when you go off of accelerator into either your node or across node are slightly different, especially about who's originating the communication. This is not intended to replace things like HPL or HPL MX or mixed precision or other things or fine-grained unit tests. This is more about being able to test the entire system and the relevant portion of the software stack. One of the challenges is the benchmarks that you develop can span many, many years when you have these large-scale, leadership class procurements. And so we've seen it where we spec a given AI benchmark, and then by the time we start citing the system, that benchmark is trivially small. It fits it within a fraction of the accelerator, and so now you have to go through some magic hoops to try and figure out how to actually test at scale. So we want something that's actually scalable in that respect. It's also important if we want to measure the vendor's software stack that we want to make sure the model is actually going to train to convergence or does inference correctly. We don't want to just flip bits because we can do that with a number of ways. We want to actually make sure the tools that we get work. And we want to capture what happens when you start to specialize the hardware. We've heard about tensor cores and matrix engines. We need to know that those are being used effectively. Are we getting what we paid for? What percentage do we get? And so, we've shown us that, modular sort of kernel-driven benchmarks where you just test the matrix engine miss key integration points that can cause a lot of pain and suffering when we cite leadership class systems. And I would say that for a long time, the HPC community has included things like the MPI software stack and the compiler, and that is a gap we've had in previous AI benchmarks. So we're going to cover that. And then, finally, I would say that, we assume that the vendors are going to make sure that the largest language models are going to perform well. That's where they're making their money. So those tools, the tools and the hardware will work well where the vendors are already getting paid. So we need to make sure that the scientific community is well served. As I said, there's a big diversity or big divergence in the maturity of how we test the relative stack. So on the left-hand side of the diagram, we can see sort of the things that are covered in green that are part of the traditional HPC stack. And that's over from the compilers, the runtimes, MPI, math libraries, specialized libraries like Raja and Cocos. And then we have suites of benchmarks that are either proxy apps like AMG Encrypt Key or HPL, OSU benchmarks, HPCG. Those are great. On the right-hand side is sort of where I think we are at in the AI community. We have partial coverage, and it's really incomplete. And so this benchmark that I'm going to propose is not intended to solve all of them. It's to cover one key gap. And really, we need to be able to, again, as I said, capture some of the important things that are not being covered. And so when we talk about the HP or the AI stack, we have AI accelerator libraries from all the three major vendors here represented. I will tell you that NVIDIA's libraries were not always great, and in fact, for some SciML problems, they still are not great today. Even just a few months ago, we found that there was a huge gap where for a scientific compute kernel of a 3D volume, they got 1% peak efficiency until they recoded it. All the way up to sort of the communication libraries, we've seen how that's challenging to scale. And then the community tools, like things like PyTorch and TensorFlow, we want to capture some of that, but we don't necessarily want to optimize that as much. And then we also want to be able to say, if we have new AI methods come on scene, can we know that the benchmark we put together is still relevant? Okay, but doing this is hard. So we've seen things like HPL mixed precision, where it tries to do basically a traditional HPL thing, but leverage some of the tensor cores. That's great. But when we have, in the AI space, there's a unique challenge because it's been hard to formulate a problem that is generative and deterministic. So if you were to just say take a model, let's say GPT-3, 175 billion parameters, and say we're going to use that as our benchmark, again, today that may not fit on any system we could have. It does today, but if you picked that 6 years ago, it may not fit on most systems. And then if you go to actually start saying we want to have a simulator of the new hardware we're putting together, it certainly won't run on that. And when you get 40, 60, 100,000 nodes, it's a trivially small problem. So AI models or AI problems are uniquely determined by the model size, the data set size, and that's a huge problem. Do you have to carry around real world data, terabytes or petabytes of data to run through this model? The memory capacity accelerators of these things, and they all matter. And we would really love it to be relevant for RFIs, star forward, efforts like path forward, all these different things where we want to do this, RFPs, and finally procurement. So we're particulating the scaffold benchmark on a particular class of problems, which are the modeling and simulation of physical systems. So I have here an example of a Rayleigh-Taylor instability where you have two fluids that are mixing, and that is, I think, representative of a large class of our scientific problems, not everyone, of course. But what's interesting is if you think about the interface between the two materials in this example, that's where a lot of the interesting complexity lies, and you want an AI method to be able to do well there. So again, going back to the inspiration I saw at R-CCS, it must have been 5, I think, where they talked about how to train visual models on fractals that they were able to generate. I said, hey, could those fractals be a generative deterministic data set that you can do on the fly? And if I squint hard enough, I think that the fractals kind of look like the complexity we see in the boundaries. This is, or sorry, not the boundaries, the interface between the materials. This is not one for one, but if we think that that's interesting, then if we can make a benchmark that is trained on a generative data set using fractals, we now actually have a very interesting opportunity to have a scalable benchmark. So what is this going to look like? The benchmark is called Scaffold for Scale-Free Fractal Benchmark. It is a UNet-based architecture. You see, and the thing is, UNets are still in popular use in a lot of AI problems today. You heard about one of them yesterday at the DOE MEX meeting. We saw some from our Argonne colleagues. So they're still very common, and they're probably the largest, most popular architecture outside of large-scale transformers. So we're going to try and represent physical simulations and other inverse sort of design problems and things like that. So the task we want to do is the semantic segmentation of a 3D volume. So we're going to give it a large volume where each sample is large. We're going to do a UNet architecture, and we're going to generate a large output volume. That also helps us stress the I/O of not just the system, but also not just the accelerators, but also the system. You can think about how this captures a couple types of data parallelism. I'll show you more, but later, but mostly spatial and data which are under-tested with LLMs and transformers. It definitely has accelerator communication beyond the standard all-reduce. And the key thing is that you can make this problem sort of arbitrarily large, and most importantly, it has a self-labeling learning task that we can do, where we can basically take a fractal, say each class is interesting, and do a semantic segmentation, so we can actually be able to generate as much data as we need. And the intent is that this is a scale invariant problem. What I mean by that is if we run for a small problem or a large problem, if we're correct, we're going to be able to say you should be able to train to a dice score of 0.7 or something like that. And if so, then you can sort of set the benchmark for a system size you can't even run today, but you will in the future. Where if you say make this much, much larger, we want to be able to know that we'll actually be able to train to that. That is an open question, and I should have said early, this is what I consider sort of a work in progress talk. We have a lot of this done. We actually have code running for all this. The data you see is real, but we haven't actually answered this one question, and I'd also like some feedback on the challenges that I'm going to present in a few slides. So how would this work? Is you have this UNet where at the bottom you have an 8-cubed bottleneck layer at the very bottom, and you can sort of set your problem size to be the sort of the depth. It's this this in parameter here, which so if you have n equals 7, your volume size is 128 cubed. And then you can basically procedurally generate how big your model is, and you will also see how we generate the data set that accompanies it. And so there's sort of an understandable amount of data, or sorry, compute work to do, and this is the key thing. So like HPL, you could do this U5, or sorry, n equals 5, where it's a fairly small 32 by 32 problem, or 32 by 32 by 32 problem, or you could start n equals 12 if you want to consume a huge amount of a large-scale leadership class system. So that is one of the key components of what makes this scalable. As I said, one of the key things we want to be able to do is capture a communication pattern that is underserved in the community. So this is sort of the menagerie of different parallelisms you'll see in the AI space. Wahib actually captured most of these here, but I'll say that ML, or large language model training captures sort of the top 5, as he said there. But what it really misses is sort of the spatial parallelism, and that isn't where there's an opportunity for something like Scaffold to be able to capture both data and spatial parallelism. I will also say, if you pick a fixed size model and you make your system larger, most of these parallelisms for LLMs goes away, because it now just fits on a single node. And so again, this is why you need to be able to make the problem larger as you go along. This is what I mean at the bottom where I say GPT-3 is not always large these days. Depends on the size of your system. Okay, so what is the intent and how will this work? So we're almost ready to release this publicly through an open source mechanism. So that will be where it lands. It's not there yet. But the idea would be for anybody could then go and check out the Git repo, clone it, pull it down. They then are able to set the problem size they want to play with. So n equals 7, that's going to be a 128 cubed volume size problem. And then they can choose the number of fractal classes they want, the number of fractals per sample as they compose it, and I'll show examples of all this in the next few slides, and the size of the data set. And so they can play around with benchmarking their system, but more importantly, if you're using this for procurements, you could tell a vendor, I want you to use this set of parameters, and especially if we're able to achieve a scale-free or a scale invariant value, if we know we're going to train to X final value, you must hit this for acceptance. So in theory, it could actually be used for acceptance testing. Then we're going to go and deterministically generate the data set on your system. We'll probably, as we deploy this, actually have cached sizes of these where it's easy to pull down, moderate sizes. But if you, again, need to go to a very large problem, there's a way to just run a bunch of parallel compute and generate all the data yourself. And as I said, it is self-labeling. And so then there's a training loop that trains it to convergence. And again, if we're right, we're going to be able to say you will train to a fixed value for every size. What does this look like in practice? This is an example where you have a training volume. This is a 514, the sample number that we generated. We have a handful of fractals in there. They are all false colored. Then you have the labels, which is what you actually want to do in the middle there. Sorry, the labels on the right-hand side, and then you have the prediction for a trained UNet on this example here. And I'll say it's important in this test that we don't actually provide the color, so it can't do segmentation based on the color. It actually sort of has to understand where it is in the 3D plane, or the 3D volume, and then and how those points align to their different iterative fractal classes. So how do we get there? Where's step 1? We need to actually create a bunch of fractals. So using the code, we pulled the Recon code that we started from with our collaborators, and we say here's a set of fractal classes. This is fractal class 1 for a 2D example, and then there's 12 parameters that the code is able to manipulate. So you can generate a large swath of unique instances of that. And so that's step 1. So we have a bunch of fractals in point clouds now. Then you're going to say we want to start composing these into a problem size of fixed difficulty, where in this example we have 3 fractal classes, 0, 1, and 2, and we now generate a sample, which is a point cloud of all 3 of those, and that's on a range of -1 to 1 space and continuous space. We then need to voxelize this, and this starts getting determined like how hard your problem is. You sit there and say, well, I was a problem size of n equals, or I think it was n, equals 5. That'd be a 32 cubed volume, and you would voxelize that fractal cloud onto that size there, all the way up to, in this example, 256 cubed, and there's 10,000 points in each of these examples here. What you'll notice is that there's a lot of collision here and a lot of aliasing as you map the point clouds onto the volumes. But again, you can sort of pick, you can see the behavior as you map from point clouds to volumes. So there is a bit of a challenge, and this is one of the first things I'd love some help on if people know, if people can help us out here, is that if you think about how this works with, this is just one of the fractal classes, we have 1,000 points per volume, 5,000, 10,000, and 50,000 points per volume. What you'll see, or what we've seen in some of the generations, is it starts to sort of have a lot of the points that are sort of on the outside of the structure, and then as you go iteratively create new points, it tends to fill in. And what that means is it's not getting larger in sort of the maximum distance between any point on the outside. The minimum distance between points is getting smaller. It's sort of finer resolution. Now that's interesting, but it sort of means that we're getting increased density, or sorry, we are increasing the point density. We're not increasing the sort of total size of the problem in the fixed space. And so we have to think about that, and I'll show you on the next slide. The other alternative is if it were to fill out, where you think about it sort of growing in space where points sort of wander away, you'd get a larger and larger size example of the problem. So when we look at this, what's interesting is on this plot here, we're showing how many points we've generated on the x-axis, and this is a log-log scale. So we're going from a couple up to 10,000 points. And what's the minimum pairwise distance between any of them, or between all of them? And it's for, what is it? We have 5 different classes there. And you can see that as you start adding points, we can add, 2 orders of magnitude to points. If you look between 10 to the first or 10 and 1,000, and you can see like red and purple really dramatically get closer, where the 2 points that are closest to each other get really, really close. They go down by 5 orders of magnitude in terms of total minimum distance. And so those rates are they're very different rates in which those are increasing. So what that means is when we map that onto a fixed size structured grid of a 32 cubed voxel, or a 32 cubed volume, you get a lot more aliasing, and it's different for each fractal class. I'll come back to this a little bit more in a minute. So this is just showing, again, what happens for the composition at 4 different point sizes when we say we go from 1,000 to 50,000 points for these 3 fractal classes on a 128 cubed volume. And when we look at this, so this challenge here is, as we look at the number of points per fractal, the percentage of the volume that's occupied is really small. Now you say, of course it's really small. You're increasing, the volume size by a uniform parameter, so it's cubically the number of points in that volume and go up cubically. But it turns out this is way below sort of if there's never any overlap, if you just randomly filled that volume, you'd have single-digit percentages for some of these things. But what we see is these curves really taper off, where there's a lot of aliasing because you get this increasing fill-in pattern where points get closer and closer together, and at a fixed volume and a fixed resolution of that volume, they just map into the same voxel, and so that's okay. But what's not clear to me is as we go up to larger and larger, will the model learn as effectively? So that's really the open question. We just haven't had a chance to sort of run through it and see as we get to like 2K cubed volumes. It'll be interesting to see because it'll be such a small percentage of it's occupied. Is it a huge problem? We don't know. This is an open question. So this is actually training of the model here. So this is for up to 100 epochs. We have a 64 cubed problem size on the left, 128 cubed problem size on the right. The dice score, which is a great thing because it's sort of how many of the points overlap, and it doesn't matter on the occupancy of the volume, so that's cool. And what's great is that with 5 fractals per sample, the dice scores look pretty close, right? So we actually have 4 examples where there's 5 fractals per image and 5 fractals in the data set for blue and 50 fractals in the data set for orange, and you're just composing 5 of them per volume. So you get a bunch more diversity. But the shape of these curves and the absolute value of these curves is actually fairly similar, which gives us hope that we can get that scale-free behavior where the dice score should not depend on what volume size problem you're working with. You obviously have to have the right amount of data, but. Okay, so one more challenge here is that, again, So the open challenge, as I've been saying, is we want to make sure that we can train to a constant dice score for this example here. And when we get to that very small percentage for larger and larger, we don't know if this is still going to happen. And as I said, I'm just sort of recapping here, right? The minimum pairwise distance, you get 2 orders of magnitude more points, and you get 5 orders of magnitude decreased minimum resolution. You cannot just make your grid that much finer resolution without making a huge problem size. So of course, anybody who's done their HPC background and homework will say, well, why don't you use something better than a uniform grid? Why don't you use an octree or some sort of adaptive mesh refinement where you put more mesh squares, more voxels in the areas you need them? That's cool. That's how you do it as actual production code. But that makes it much more challenging for the AI model to learn. It also makes the benchmark much more complex, and I'm not sure that we need it, because the goal isn't necessarily to test, the absolute problem. It's to have a benchmark for the software stack and the hardware. Sorry, both. So I'm not sure that we want to go there. And again, in the spirit of getting feedback from the community, are there any other sort of generative classes of problem that we can use? So we thought about a week ago about could we use like a 3-body pendulum to fill in some of the data, or other chaotic systems where we can sort of generate and know the answer. All right, to summarize, we're proposing this new benchmark. It is a complement to the things that we already use, but it's really intended to capture unique characteristics of the AI for science applications, particularly these that are well represented by the modeling and simulation of physical systems, as well as sort of all of these classes that use UNet-based architectures use UNet architectures. It's intended to capture enough of the vendor software stack so you can have confidence that you're able to get a system that is cited that works well. And the key thing about this is because you generate the data and you know how you generate the data and you don't have to ship petabytes of it, you can go from like lab bench or simulator all the way to leadership class systems. Especially if we can make sure that we know that you can have a targeted training outcome that can be deterministically calculated, then you could actually use it for procurements and acceptance tests as well. So that's the plan. We're almost all there, but again, I welcome any feedback and questions. Thank you.